All right, welcome everyone. So this is our 10th live stream geometry session. So we have 2 people here with us currently, and I'm sure more are going to join later. So the problems I chose are from the Sharygin Geometry Olympiad. So that's a geometry contest in Russia. I believe people scan in solutions through the internet, and it just ended on March 1st. So I should be able to discuss the problems since people have already been doing it on the internet. But it's a very nice contest that's geometry only. So that's pretty cool. And I also took a few other problems from the Brazil Math Olympiad and the Swiss team selection test. So I'm going to hop right into it. All right, let me share my screen. All right. So here's the first problem. It's from the Sharygin this year. It looks really simple, but it was one of the later problems. So we'll see how easy or hard it is. So we have 2 circles that are internally tangent. So this is usually how I draw it, or this is usually how I do it. So I draw a line, and then they're internally tangent at A. So let me do it like this, something like this. Those 2 circles are internally tangent. And then we have a chord of one that's tangent to the other. So I'm going to change the names of all these points in just a second. And we want to show that this circle, so the circle BOC, bisects the segment AK. So, all right, let's change the name of a couple things here. So hide. And these are B and C. I'll call this B. Whoops, I didn't hide this. Whoops. That's B. That's C. This is O. I'll just leave the other 2 points the same names. We want to show that circle bisects AK. Okay. Let's see. Interesting. So if we move this around, well, that means OE is perpendicular to AK, right? Let me maximize this. Oops. Oh, I think because I hid B, I don't have control. There we go. All right. Yeah, it looks like an easy problem. It was later in the contest. Let's see. So angle BKA is half of angle KOA. We want to show basically angle BKA is equal to angle KOE. So that's kind of like saying, maybe it might help to draw the other tangent. I don't know. You beat me to it. You're faster than me. Or I could just unhide the other one. So yeah, maybe. Yeah. something like this. Let's see. I wonder if that makes it easy. We want to show angle OEK is 90. Yes. So yeah, because the perpendicular from the center to the midpoint bisects the chord. We know angle OAF is 90. I don't know if maybe that helps. Maybe we have similar triangles. Is yeah, OE and F look yeah, they would be collinear. Is it odd? Yeah, we have to show OE and F are collinear. Maybe that's just power of a point or something. AK is perpendicular to OF. Yeah, because by symmetry, because those are both tangents. So yeah, we have to show OF passes through E. We know AK is perpendicular to OF. Yeah, how do we show OE and F are collinear? See. So if E prime is the intersection of OF with AK, oh, that's a good way to do it. Okay. I like it, thinking in reverse kind of. So okay, so that would solve it. So I'm going to start just writing up the solution here. All right. So let me call that E prime. So yeah, it's not super hard, even though it's number 16. Okay, so write it like this: let the common tangent at A meet line BC at F. And then let OF, so FK and FA are tangent. So OF is perpendicular to AK. All right. And then let OF meet AK at E prime. And then we can apply the argument that I3435 said to show that BE prime OC is cyclic. So one second, I'm just going to look at how he phrased it. So we have OF times E prime F is equal to, or FE prime, yeah, times FO is equal to FA squared is equal to FB times FC. And so, yeah, basically power of a point finishes it off. So, or we probably could have done it the other way using the radical axis theorem, but it doesn't matter. Same thing. So FA squared is equal to FE prime times FO. That's pretty well known. I'll put FB times FC in the beginning here. And so that means that BE prime OC is cyclic. So E prime equals E. I'll say E prime equals E is the midpoint of AK. Yeah. And that basically solves it. I'll just write it out. All right, now I will move on to the next one. I wonder where everyone is today. All right, here's the next problem. So this is also from the Sharygin. It was number 7. So I don't know if they're in order of difficulty or not. I thought they were, but it's possible they're not. Okay, so it's tangent at E and F. And then M and N are on EF. So CM is equal to CE, and BN is equal to BF. Okay. I don't know if it's worth keeping the circles. I'll hide them in the end just in case they add some kind of insight. Let me hide this. BM and CN meet at P. And we want to show PI bisects MN. That's kind of interesting. Let's just check that out. Yes. So maybe we could let PI meet MN at point D, and we want to show D as the midpoint. That's one way to look at it. Yeah, let me hide those circles. They're kind of messy. All right. This looks interesting. So these triangles are all similar, I think, BFN, AFE, and CEM. And I think CM is parallel to AB and BN is parallel to AC, it looks like. That should just be an angle chase. See, maybe we could use projective geometry here. I don't know. So if we project, like we project MDN infinity through P onto BC, I'm thinking. Not sure about that. Just angle chasing. Okay. PI bisects MN. It almost looks like, no, PI can't be parallel to CM. That would break symmetry, basically. Yeah. So there's a solution with just angle chasing. That's what Arabian math is saying. there any like congruent triangles here? Let's see. Yeah, I wonder. Let me check Discord just to see, because usually there's more people on at this time. Problem. PI bisects MN. Yeah, this one feels harder than the previous one. Let's see. I wonder if we like extend BN to meet CM at a point. That feels like it might be useful. And we'd have like a big isosceles triangle. Do they meet on AI? No, but there is like a parallelogram. So basically we want to show like, yeah, we want to show D as the midpoint. We want to show GB as like perpendicular to MN. AM. Oh, do they meet on the line AM or A in the midpoint of BC? Yeah, they will pass through. Yeah, they will pass through that because it's a parallelogram. So yeah, we could draw that and yeah, we want to show that's perpendicular. That would solve the problem. Maybe there's some cyclic quad or something. I don't know. Yeah, this is a cool one. I like this. Very centric. I believe you. I don't know Barry very well. I only read it very briefly, but looks like a few more. Looks like Irijon has popped on, and Arabian Math is back. Yeah, if you guys type up the whole Barry solution, I'll type it out here. But yeah, I don't know it very well. Let's see. Hey, Irijon. Yeah, thanks for joining. feel like there has to be like a projective solution. It just feels like it. The A in touch point. Okay, so DNM, if that were D, okay, so let me draw a couple things. So that's an X circle, you're saying. Let's see. It's not tangent to BC. And NJM. Oh, whoops, my bad. No, you're right. Is that obvious? Let me think about that. Can I switch name? Yeah, sure. I can switch the names of B and J. Hold on just a sec. Because GN is GB plus BN, which is GB, which is AC plus BF. Yes. So that proves that that is indeed, yeah, you still have to show GN and GM are tangent, right? But that's trivial through an angle chase. So, okay, so that seems like some good information. ABC and GB, yeah, of course, yeah. Okay, so we know that that is an X circle, CNM, or I'm sorry, DMN, and from there, can we show J is the midpoint of MN? Let's see. So GD and P are collinear by a homothety, it looks like. Not homothety. I guess I was thinking, so also DI in the center of that big circle are collinear. So if they're not collinear by homothety, yeah, why? Oh, Cheba. Trig Cheba or normal Cheba? Just let BC intersect MN to be T. Okay. I'm just thinking that through my head. So in terms of GBC, that makes sense. I'm trying to. Okay, so I'm thinking of Arabian Maths, what he's saying. So if we let the intersection point be T, then B, C, D, and T. We want to show they're in harmonic conjugation. Is that obvious? I don't see it yet. AD, BE, I agree, AD, BE, and CF are concurrent, and so I agree those are, I agree that T, B, D, and C are in harmonic conjugation. And so how does it follow? Yeah, I3435 was suggesting using barycentric coordinates. And then GD, BM, and CN. I don't know how I didn't see that. Okay, so because T, B, D, and C are in harmonic conjugation, it follows that CN, MB, and GP have to concur. Yeah, it's using harmonics in like a tricky way, because it's like you have triangle GBC, and you have one point that's on it, and you have two other points that are on the extensions of the sides, and you're using harmonics in that way, kind of, is what it sounds like. Okay, so once we know GD and P are concurrent, it also looks like this is a right angle, maybe. I'm not 100% sure. You always beat me to everything that I see. Let's see. Let me measure it. Yeah, it's not a right angle. IH is parallel to GP. So this is kind of like the IN lemma, right? So I'm trying to think why. I know IH bisects AD. So yeah, IH passes. So AH equals HG. Oh, and IH bisects AD. Okay, so IH is parallel. Yeah, IN lemma. Yeah. Okay. So I see why that's true. Let's see. Hey, Rodrigo, thanks for joining. Sorry, I missed it. All right. So IH is parallel to GP. I agree with that. So reflect I across H. Okay, hold on just a sec. So I prime. That would be the in-center of GBC. Okay. But yeah, I mean, that's true by symmetry. Since I is the in-center of ABC, I prime is the in-center of GBC. Let AH intersect EF at S. Then DI and S are collinear. That's is that like the Iran lemma? But yeah, no, I know that's a well-known lemma. Okay. So yeah, there's a lot of stuff going on here. Have we done enough to finish the problem? So DI and S are collinear. I prime is the in-center. Project something through I, maybe. Yeah, I was thinking of projecting M, N, and J through I. No. Let me try something. Yeah, there's a lot going on in this diagram. Let's see. MNJ projected through I. What do I project it onto? BC? Really? That seems tricky to me. Like, it's hard to, I guess I'm trying to see like how that would help, or what that would end up with. Through P, yeah. No, so yeah, I've always been wondering, like where does IP meet BC at? And then like also you'd have, so you'd have to project like, oh, maybe, yeah, it looks like it might be the perpendicular from A to BC. No. But then you'd also need like the parallel from through I to MN, which is also like the perpendicular to AI. So yeah, there would be a couple different points in that. Do the problem in terms of GBC. So GBC is a triangle, and then we have an X circle, and then this would be like the reflection of that triangle over H. And yeah, I mean, we could do it in terms of GBC. R is the midpoint of GP. Then R, H, and J are collinear. We have a lot of, but we want to show R, H, and J are collinear, or do we know that? R, H, yeah. Well, if we knew J was the midpoint, then we would know R, H, and J are collinear, but we're trying to show J is the midpoint, right? But 2IH is equal to GB. That is well known. Hold on just a sec. So IH is equal to 2GD. I think I see why that's true. Hey, John, thanks for joining.
Hello, Michael. I'm sorry I'm late. I was having lunch. I'm sorry.
Oh, no worries. Okay, so oops. So I'm trying to think about this. So let me do this. So if I reflect D across H, so I get D prime. So GD is the same as AD prime, right? And so it's kind of like we want to show AD prime is twice IH. No, I don't think GD prime is twice IH. That's not, but yeah, there's just a lot going on in this figure. Let me go back to the chat. Whoops, sorry. Oh, 2I prime H is GB. Yeah, that makes more sense. Or no, not. Yeah, IH passes through the midpoint of AB. So, I mean, if we extended IH to meet AB, then that distance would be half of AD prime, right? So KH is half of AD prime, but not IH necessarily. But IH is parallel to DG. I agree with that. Okay, so let me see. How can we show? Yeah, I agree. IH is parallel to DG. No, you don't have to apologize. It's all right.
I'm sorry, how did you define point H?
H is the midpoint of BC.
Oh, nice. Thanks.
Yeah, you're welcome. Yeah, if we can show RH and J are collinear, that would solve it by the Gauss line. Yeah, there's a lot of stuff going on here.
What is the Gauss line like? Can you define it?
So suppose you like start with the quadrilateral BPCG, right? And then so M and N are where the extension of the sides meet, right? So you have BPCG, and you extend the sides to meet at M and N. The theorem, it's a theorem basically. It says that the midpoints of, so if you take the two diagonals of BPCG, so the midpoints of PG and BC, so that's R and H, and the midpoint of MN, which is J. Well, we want to show J is the midpoint of MN, but if it was, the three midpoints are always collinear. That's the Gauss line, the theorem of the Gauss line.
Very interesting.
Yeah, that's a cool one. I did a video on it a while back. So if you look through my channel, you'll find it somewhere. So he said, so GR is equal to 2 I prime H. Okay. Okay. I'm trying to see how we get to this final. Eventually, we're going to have to get to this final thing. AB intersects CN. So if you take AB intersects CN and AC intersect VM, they're collinear with I. That sounds very plausible. Yes. Yeah. All right, I'll keep that in mind. Yeah, and it's also going to be, yeah, parallel to, yeah. Let's see, how do we get to that final? I feel like there's a lot of structure in this configuration, but eventually we have to get to PI bisecting MN. So somehow, I'm just trying to think how we would eventually get there, what a sort of strategy would be. I mean, we could show, there's so many different ways. We could show GI prime and J are collinear. We could show R, H, and J are collinear. We could, yeah. Yeah, we know these two are parallel. One sec, guys, I'll be right back. Oh, yeah? Spit it out. I'll be right back, but yeah, type it in the chat. It'll be interesting. All right, redefine J as the midpoint of MN. Okay, we want to show PI and J are collinear. All right. And then we'll see. Let's see. Okay. And then this. Oh man! So you used a different problem. Interesting. I'm gonna draw it out on paper. Let's see. We have a triangle ABC in center I. DEF is the contact triangle.
Michael, have you already proved that CM is parallel to AB?
Yeah. So yeah, we've shown CM is parallel to AB, BN is parallel to AC. Yeah, these triangles are all similar. Isosceles triangles, BFN, AFE, CEM, and GMN. Yeah, and this is a parallelogram. Yeah. So yeah, we've gotten to all that.
Nice.
At least I've proven it in my head. But let's see. So I3435 has an interesting way of doing it using an idea from a different problem. So I'm going to check it out. H is the orthocenter of triangle BIC. P is the foot from D to EF. This is kind of like a Sharky devil. If the midpoint of EF is N, the midpoint of DP is N star. and you have the Gergonne point. Okay, so it's stuff with the Gergonne point. Instead of the in-touch triangle of GBC, we were doing it on the GX touch triangle. So you're saying that your theorem also kind of applies in a way to X circles instead of in circles? All right. Let me first see if I can, I'm first going to spend a little bit more time seeing if we can find another solution, but otherwise I'll try to type up that one. Yeah, post that theorem on the Discord. I think that would be pretty useful. Was that in your book that you wrote?
Wait, this guy wrote a book?
Yep. I3435 has.
Oh gosh.
Go to the very beginning of the chat. The very first link that Arabian Math posted. It's a book he wrote. It's really awesome.
I entered like late. Could you send again the link?
Yeah. Just a second. So yeah, I just typed it in the chat. It's like a 96-page book he wrote. It has a bunch of properties of the ortho center, the in center, a lot of really deep theorems in it, and like useful configurations. So yeah, I think it's incredible. So yeah, I'd recommend all you guys check it out.
Oh gosh.
Yeah.
Oh gosh. I once wrote like something like a 2-page article about orthocenter, but he wrote on 96 pages about orthocenter and triangles.
Absolutely. So yeah, thanks for sticking with that. Thanks for sticking with that book, I3435. I'm sure, yeah, a lot of people really like it. All right. So
really nice.
Yeah. So PI bisects MN. So yeah, I guess if we drew the X center, we kind of want to show G, J, and the X center are collinear. I wonder if we can like apply, because if J were like, I'm just thinking. Let me try something.
I'm sorry, was it I3435 or the Arabian Math who wrote it?
I3435 wrote the book. So, yeah.
Pretty nice, pretty nice.
Yes, absolutely. Let's see, PI bisects MN. Yeah, I'd like to project through point P. What if we So yeah, I mean, if we were to project through point P, R is the nasal point of triangle GBC. So I see it lies on one of the Chebians that you need. Is it? I would definitely believe that. I'm just trying to think. Okay, so R is the nasal point. So is it like a known fact that the nasal point, the midpoint, and the midpoint here would be collinear? Maybe that's like a well-known idea. Oh boy, USIMO problem. You guys know a lot more than I do. Let's see. How did you know that R was the nasal point? Is it from that USIMO problem, or was there another way that you got to that? I see GD as one of the Chebians, obviously for the nasal point. But is it obvious that the other that it lies on the other Chebians for the nasal point? We can finish off by homophily now. Let's see. So I'm just thinking here. Yeah, type out the details. Okay. You haven't proved it yet, but yeah, let's see. So yeah, for those of you that don't know, the nasal point, if you draw the segment connecting each vertex of the triangle to the X touch point, so like D is the point of tangency of the X circle to BC, and then you do it for all three vertices, they concur at the nasal point, which Arabian math is saying is R. Okay, so you're saying if we could prove that R is a nasal point, then that would mean that RH and GI concur at point J. Right? Okay. So yeah, we'd still have to show that those concur. But H is the midpoint of II prime and R is the midpoint of PG, so that would basically, yeah. So once we know R is the nasal point, then is it a well-known fact that RH and GI prime meet at J? Well, so we know GI prime passes through J. Is it well known that RH passes through J? Yeah, is it a well-known fact that RH passes through J? Yeah, GI is the angle bisector, so it's going to pass through the midpoint of MN. But RH, is it well known that that passes through the midpoint of MN? It seems like it would be a very useful fact, so I'm guessing someone probably knows it. But yeah, I don't. Oh, it's the Gauss line. All right. So yeah, the problem's reduced to showing R as a nasal point. Wait, do we even need? We don't even need the nasal. Yeah, yeah. Okay. All right. Let me just. How did we define R in the first place? Okay, R might not be the nasal point. So R was the midpoint of GP, and we can redefine J to be the midpoint of MN. So by the Gauss line, RH and J are collinear. We also know G, I prime, and J are collinear. And we can prove that those are parallel. Okay, I think that's the simplest solution. Yeah, so I'm going to start typing it up. Sounds good. All right, so let me delete some of the extra stuff we added. I think that's a fairly simple solution. Yeah, I like this one. It is pretty nice. So I'm going to move the diagram here. So yeah, really, we don't even really need the X circle, right? As long as we know like the IM lemma. Let me see, what did I just delete here? Yeah, I mean, we want point. Let's see, what else can I hide? Maybe just that. Yeah, okay, so yeah, but really we just need the IM lemma. So I wonder if I could just, I'm going to delete AD prime. Okay. All right. Yeah, we don't need point S. We don't. Yeah, I'm going to redraw in some of these lines later. Okay, so yeah, I think the Gauss line is really what makes this proof tick. I think that's really the key in many ways to getting this to work. Okay, so so basically, first we want to show BN is parallel to AC and CM is parallel to AB. That should just be a fairly easy angle chase, I think. So we have the text box used to be draggable. I don't know why they changed it. But yeah, I'm just gonna move this way over there just so we can see the text box. Or just so the text box doesn't cover it up. There we go. So first of all, we have angle BNF is equal to angle BFN, which is equal to angle AFE, which is equal to angle AEF, which is equal to a lot of equal angles, and these prove that a bunch of lines are parallel. Let me just change this a little bit. Hopefully it won't cover up the diagram still. So, okay, so that means that BN is parallel to AC, and CM is parallel to AB. Don't need that. Okay, and then extend BN to meet CM at point G. So ABGC is a parallelogram. All right. Let J be the midpoint of MN and R be the midpoint of GD. All right. Okay. Let I prime be the reflection of I over H. Okay, so by the theorem on the Gauss line, R, H, and G are collinear. I haven't even defined H. Okay. The Gauss line, so that's in a previous video. I'll say on quadrilateral BGCP. We have R, H, and J are collinear. I haven't even really shown that. Do we need that PRG passes through D? I don't even know if we need that fact. But I'll check it out later. Okay. So R, H, and J are collinear. And then also G, I, and J are collinear. So we do need that fact. Okay. Yeah, because the IM lemma. Okay, so so first I'm just going to write out a few more steps. So angle BNF is equal to angle CME, implies GNM is isosceles implies, or actually first I'll say this, by symmetry, I prime is the incenter of triangle GBC, since I is the center of triangle ABC. Okay. And then we have angle EMF is equal to angle CME, implies GM equals GN, implies GI prime and E are collinear, or GI prime and J are collinear. Okay. So I'm going back to showing and then, yeah, so we know IH is equal to HI prime, PR is equal to RG. And so to show IH, we have to show that's parallel to GD. So we have to show G, yeah, we do have to show that those are collinear. That's using the harmonics argument that you guys mentioned, right? I wonder if, let's see. Thanks. I don't even know how to type, so I kind of think I type more slowly than a lot of people, but I grew up in Florida and they don't teach typing there, so I never learned it, but all right, so how do we show that D lies on the segment GRP? It's that, I mean, you could say it's like that harmonics argument. So if MN meets BC at a point T, then B, C, D, and T are in harmonic conjugation. And then, yeah, I'm forgetting how, let's see. Basically, that means BD, yeah. I'm trying to think if there's like a simple way to say that. Let's see. So yeah, maybe, yeah, I'm thinking by Cheva. Okay, so I'll just write that out. So BECF and AD concur by Cheva. So now we're using projective geometry. And that implies that CN, BM, and GD are concurrent. Thinking about that. So Yeah, because we can take that ratio and we can project it through P. So I'll write it like this. And then from there, that means that GD, BM, and CN concur. So concur. So see second video on projective geometry. I forget which number that is, but I did on my channel. So G, R, D, and P are collinear. Okay, we're almost done here. I'm just trying to type out all the steps. I think that should be PD. Yeah. Or I guess you think it should be PD, BN, and CM? But it's the same. I'm sorry, this cut off a little bit, but G is this bottom point, right? So that's the same. I guess it's the same segment, right? All right. Oh yeah, I guess it's sometimes it just gets cut off, and okay. So oh no, it's all right. Yeah, it's so weird. Okay, so by the IM lemma, IH bisects AD. IH bisects AD. I'm not even going to draw that in. But then we also know IH equals HI prime. And so yeah, I'm just trying to, yeah, so we want to show IH is parallel to DG, but if IH passes through the midpoint of AD and H is the midpoint of AG, then IH is parallel to DG, okay? I'll rewrite it like this. IH passes through the midpoint of AB, and then H is the midpoint of AG. So that means that IH is parallel to DG. And then also we have, since IH is equal to HI prime and PR is equal to RG, then that means IP RH and GI prime occur. So all right, I like it. This is a nice one.
A pretty difficult one.
Yeah.
Actually, I didn't understand things because I don't know projective geometry yet, but that's fine.
Yeah, no,
Do you
projective
have more problems?
Oh, what?
Do you have more problems?
Yeah, no, this is not the last one. I'm gonna keep continuing until 1. So as long as you guys want to stay, feel free to leave whenever you want. But yeah, I'm gonna move on to the next one.
Nice.
All right. So yeah, so 10 more minutes, and then yeah, thanks for joining I3, 4 through 5. So we have a triangle ABC with.
This is from Brazil. Pretty
Yep,
nice.
I picked it.
Pretty nice.
I knew you would like Brazil. That's why I picked it.
I actually I've done this problem before. I don't know. I tried it, but like 6 months ago, and I didn't do it. But I'll try today. Another day. I'll try it again. Like I'll see if I can do it.
All right.
It's a pretty nice problem, I think. Oh,
yeah.
that's really nice of yours.
So we have the perpendiculars to DB and DC, or E and F. N is the midpoint of EF. Simpson line. So yeah, so basically EF passes through the altitude from A. Prove that the lines NA, N is the midpoint of EF. We want to prove that NA and NM are perpendicular, and maybe this is just the Simpson line. I will see in just a second.
It's the Juniors Math Olympiad, isn't it?
I'm not sure which round it was. It might have been. But we want to show, let's see, we want to show NA and NM are perpendicular. Whoops. Yeah, so perpendicular. So EF passes through the altitude from A, and that might be enough to just finish off the problem.
You say Brazil is very difficult.
Let's. Oh, it's not a rectangle, but let's see, midpoint. Yeah, so I'm guessing triangle AEF is similar to triangle ABC. So ANE, yeah, if we can show AEF is similar to ABC, that solves it. And I think that's just an angle chase. We need AGNM to be cyclic. Yeah, so yeah, this one, so I'm gonna write it out. The Simpson line is pretty well known, so, and it's not hard to prove either. But yeah, so I'm going to write out the proof. So we solved this one before you had to leave I3, 4, 3, 5. Okay. Let G be the altitude from A. By the Simpson line, EF and G are collinear. I think I've proven that before in my videos. And then I'm going to show triangle AEF is similar to triangle ABC. So that should just be an angle chase. So first ADEF is cyclic and AEBG is cyclic. So those are actually from the proof of the Simpson line. Yeah, AEF with N is similar to ABC with M. That was sort of the proof strategy I had in mind. Exactly. So
But
yeah, no, I'm writing it out. So so here's really the full thing. So we have angle AFD is equal to angle AEB is 90. So AEDF is cyclic. Yeah, there's just a lot of steps that we did in our head, but most of it is because I've seen the Simpson line configuration before. So angle AEB is equal to angle AGB is 90. So AGB is cyclic. And so basically we have angle AFE is equal to angle ADE is equal to angle ADB is equal to angle ACB. And then similarly, we have angle AEF is equal to angle ADF is equal to angle ABC. Wait, why did one take? This one only took 2 steps. This one only took 3 equalities, but the other took 4. Let's see. AEF is ADF is ABC, and this AFE is equal to. Oh, but because no, it's fine. It's just like the way, yeah. But anyways, yeah. So that means triangle AEF is similar to triangle ABC. And N is the midpoint of EF and M is the midpoint of BC. So basically N corresponds to M in those 2 triangles. So that means that angle ANE or AN, yeah, angle ANG is ANE. So I'll write it out. So and yeah, angle ANE is equal to angle AMB because N and M are corresponding points in those 2 triangles. And so if angle ANG is equal to angle AMB, that's interesting.
Gosh.
I had the whole idea for this proof in my head, but it takes a while to write it out. So ANMG is cyclic. See, if you've seen the right patterns before, you kind of recognize all this stuff. But if you haven't, it looks like a lot. But so.
And let me ask you something. How old are you guys? I took a while and I couldn't do this problem. And like the original solution from the one who created the problem here in Brazil uses a lot of ratios and a lot of things. Like it just
really?
did from angle chase. Yeah, really.
Yeah. I'm 28. I think most other viewers are in high school, although I think one of them is in college. Yeah, you guys can share if you want, but you don't have to.
Oh gosh.
Yeah.
You were so good at geometry.
Your Arabian math is 16. I didn't realize that. So yeah, most, yeah, it's just a lot of practice and yeah, just finding the right resources. But
You have GeoGebra.
We
Yeah.
have GeoGebra, yeah. So yeah, GeoGebra makes things a little easier. So I'm going to move on to the next one, but that was a nice little easy one.